Okay, hello everybody. I'm Sergio González Herrero from the Antarctic group of the Spanish Meteorological Agency, and I am going to talk about what, as far as I know, is the first intent of attribution of a particular heat wave event in Antarctica to climate change. And okay, to start, the peninsula opened many front pages of scientific news bulletins in early February in 2020. These news were that previous record of the Antarctic region of 17.5 degrees Celsius recorded in 2015 at Esperanza Station was broken by a new event that recorded 18.3 degrees Celsius at the same station on 6 February of 2020. But 3 days after, news echoed again that this time Antarctica had exceeded the 20 degrees Celsius in Seymour Island. However, a WMO commission refuted the latter and validated the former. But in any case, this case sparked the debate of whether these values were consequences of climate change in Antarctica. So to answer this question was not easy to answer because the records broken were not consequence only to the high temperatures of these days in Antarctica, but also to the vertical compression of the air caused by foehn effect, as shown by Chu and others. However, this record-breaking temperature was embedded in a major heat wave that struck the Antarctic Peninsula these days, from 6 to 11 February. The highest temperature was recorded on 6 February, but many other stations set their own records on different days. The highest regionally average temperature was recorded indeed in 9 February, according Era 5 reanalysis. And this 6-day event supposed to break the 6-day temperature record in many parts of Antarctic Peninsula. But the event was not only impressive from the temperature perspective, it produced also a large reach of at 500 hectopascals ever recorded on Antarctic Peninsula, as you can see in the right panel. All these unprecedented values motivate us to make the first assessment of the potential role that played recent climate change in this heat wave event. So to do this, we use mainly the Era 5 reanalysis dataset from 1950 to 2019. Due to the possible uncertainties of this dataset in the past, due to the scarce observations, we validated the Era 5 against the station and radiosonde observations, finding that although there is a notable drop of the performance previous to 1957, data can be used perfectly without reproducing large biases in our study. In fact, we also tested that we have the same results after removing the first few years. So to attribute the climate change to this event, we separate the dynamic and the thermodynamic signal of this event using the analog methods. To do it, we took the entire dataset of summer months and split it in 2 sections, one from 1950 to 1984, that we call the past dataset, and another from 1985 to 2019 that we call the recent dataset. For each day of the heat wave, we search the most similar circulation analogs using the root mean square error of the combined normalized mean sea level pressure and geopotential at 500 hectopascals. And we then created 5,000 possible heat wave events for each period by picking randomly an analog for each day and combining them. Now we can compare the distribution of temperature of our recreated heat waves in the past and in the present, and as the circulation is constrained, they have to represent the changes attributed to the thermodynamical changes. So results show that distribution of heatwave events with constrained flow circulations would have caused large warming in the recent than in the past period. You can see here the recent period in red and the past period in blue. Specifically, anomalies are now 25% higher than in the past. And the probability of exceeding a 6-day anomaly of 2 degrees here is now 10 times more probable than in the past. As it can be observed in the figure, the mean 6-day temperature of 4.5 degrees Celsius, regionally average for the Antarctic Peninsula in this event, has been unprecedented. But the 6-day temperature distribution in the present is much warmer than in the past distribution due to the increase of the temperature of the region. However, many changes undergone in the Antarctic Peninsula in the past decades, as, for example, changing the SAM index that mainly govern the circulation trends in the region. So to discard the effect of the SAM, we removed the SAM trends, obtaining almost the same results. However, when we remove all the trends in the region, the difference between the past and the present disappear, pointing to major influences of long-term regional mean warming in exacerbating the magnitude of this event, as you can see in the first panel. Okay, the study of the physical processes of this event indicated that this exacerbation was produced mainly through an enhanced compression of the air and a warmer advection, both associated with a warmer atmosphere in the region, and also in association with a Foehn effect. So in conclusion, recent changes in the atmospheric circulation cannot explain the exacerbated magnitude of this extreme event, and hence the climate change signal detected should be largely ascribed to thermodynamic changes that occurred in the region that are at the same time attributed to anthropogenic climate change by a number of studies. This study was recently published, and you can read, if you want, in more detail, the process of attribution in this study. Okay, thank you very much.
Thank you, Seki.
Okay.
People, remember that you can make your questions through the Q&A chat to Sergey, and he can answer them.
Okay. So do we have Penny online?
I'm afraid no.
Okay. I don't see her. Okay. All right, we have a couple of minutes. Is there any question for Sergey? Okay, and there's Hightour, so that's good. All right. We have more time later on, Sergey, so please stay online and we'll continue the discussion then probably. Okay, thanks very much. Okay. Once again, any sign of, I don't see any sign of Penny yet. Okay. All right, maybe we should try Hightour. Hightour, are you ready to present? I know it's earlier than in the program, but Penny Rowe hasn't shown up.
Oh, hello, David, Adriana. Yes, for sure.
Okay, very good. So Hightour Evangelista is going to talk about the detection of atmospheric rivers' impact in West Antarctic ice sheet Cryosphere 1 remote laboratory at 84 South. Okay, so Heitor, you have 10 minutes. Please share your screen.
Okay, I will share the screen now. Okay, let's see, share. Just let me see if it is okay.
It just needs to be put in presentation mode. So we can see your screen, but we can see the slides along the side, for example.
Sorry. Let's try again here. Let's try one more time. Because for me, it is okay.
Okay.
Let's see.
Yep,
Now
full
it's okay.
screen now.
Now it's okay?
Yes.
Okay. Hello, everyone. It's a pleasure to be here with you, David and Adriana and colleagues, to have a brief talk about the detection of atmospheric rivers impacting West Antarctic ice sheet at Cryosphere 1. Okay. Well, atmospheric rivers have been a topic of large debate in the literature and among Antarctic scientists. It is a relatively narrow region in the atmosphere where we have the transport of moisture and heat. Most of it from the tropics towards the higher latitudes. In 2019, atmospheric rivers were recognized as an important player in the West Antarctic melting. And in 2020, atmospheric rivers were also part of Polynia events at the Weddell Sea. And in 2021, with rapid changes in surface heights, and therefore atmospheric rivers are also associated with mass balance in Antarctica. So looking all these last publications about the atmospheric rivers, we see that its importance in the way of the melting of the ice mass in the continent, and also in the melting on the sea ice, and also in the mass balance. And besides that, if we have impacts of the atmospheric rivers to produce polynias, the atmospheric rivers also have an ecological impact, because the polynias are associated to changes in phytoplankton and also in CO2 flux. So the atmospheric rivers are more than an atmospheric process. It has an environmental impact. In fact, in this year, on March in 2022, we have a mega event in the East Antarctica, where in Dome C, Vostok, Northern Station, we observed a very increase in temperature reaching to 38 degrees. So what I address here in this presentation is what is the range, the continental range of the atmospheric rivers. Most of our monitoring of this event is mostly concentrated in the border of the Antarctic continent near the sea ice, where we have ground measurement, we have balloon profiles, but what is impacted inland the West Antarctica? So we use our data from a laboratory that we set up in the center of the West Antarctica at latitude 84, with the objective to observe changes because of incursion of atmospheric rivers in most inner sides of the Western Antarctic ice sheet. So basically, we have in this station all meteorological information. Each is run during summers and winters, and we measure the meteorological data CO2 flux and also snow deposition. And we detected the atmospheric rivers using the integrated water vapor and the integrated vapor transport models, which are the most common one used in the literature, which is an integral of the specific moisture in the atmosphere using the zonal and meridional winds, in this case using ERA 5 reanalysis. Two case studies I want to show you here, which I call your attention because they are very really interesting to be observed. The first one has occurred in 2017, when we have a very uncommon process bringing the advecting moisture and heat from the Amazonia directly to the Southern Ocean. In this case, it is a reinforcement of the South Atlantic convergence zone, which are mostly active during the austral summer. And it was reinforced with a cyclone passing here in the Weddell Sea. So we have a very prolonged atmospheric river crossing all the Atlantic Ocean, reaching until the Southern Ocean. In this event, sea surface temperature has risen 10 degrees, and it promoted the occurrences of polynyas at the Weddell Sea. The polynyas are semi-permanent open waters at the sea ice. It's just permanent, and in this case, it happened. It is well described in the literature. These two models, the integrated water vapor and the integrated vapor transport, was well described. This process in the integrated vapor transport shows that it has implications to the border of the Antarctic continent. But in the inside, we really observed the changes in temperature together with humidity and also with snow deposition. It is clear demonstrations that these big events, they are really responsible. They have an important role in the West Antarctic mass balance in its interior part. And in the second case study, we just observed a few days ago. It was on June 10th. The temperature has increased 30 degrees in the West Antarctica as the Cryosphere 1 laboratory. It is not the same event that we observed in the East Antarctica, because the East Antarctica was in March, and the advection comes from the Australian sector. In this case, it has occurred at the West Antarctica. It was the most pronounced peak of temperature during the winter time. The event in the East Antarctica have occurred just in the end of the summer season. The reanalyzed maps will capture this event with the incursion of air mass, of warmer air mass from the Weddell Sea towards the West Antarctica. We can see also here in these representations, this red dot is exactly where is the Cryosphere 1 laboratory. When we look at the anomalies of temperature, we see that mostly of the anomalies are related to 20 degrees, but we observe much more than this, something around 30 degrees. So what was the synoptic condition during this event? We have extratropical advection from the Atlantic and another extratropical advection from the southern of Pacific. It was well recognized with the integrated water vapor, and the integrated vapor transport show a much more pronounced incursion of moisture and heat from the South Pacific. A dynamic view of this process shows that it has originated in the Southern Pacific and then migrated very rapidly through the Drake, passing the Antarctic Peninsula in the western side of the Weddell Sea, reaching the inside of Antarctica, and then producing that huge impact of in the temperature in June 10. In fact, June was the warmest June ever recorded in Antarctica. So this month was especially warmer compared to other databases. Also, the sea ice and ice concentration was lower than the historical values. We also compared this event to Halley Station, which is the closest meteorological station. We observed the same peak, but in Halley, this event was in the same order of magnitude of some others during the winter, differently from the cryosphere one in the inside of Antarctica. What did we learn from this observation till now? Well, models detect this event, are able to capture this event of a very rapid increase in temperature, but not their real amplitudes. So what we measure inside Antarctica was a higher amplitude than what model captured. Atmospheric rivers, in fact, impacted the interior sector of West Antarctica, but with different frequencies from the coastal region. And the Antarctic plateau geomorphology constrains this transport of moisture and heat. Okay, thank you very much for your attention and patience.
Okay. Thank you very much, Heito. Very interesting. Okay, so let's see. Any quick question for Heito before we move on here? Anybody?
I do have one. The cryosphere one, how do you maintain this station operative the whole year? Because you said it's in winter and in terms of energy and, you know.
Mm-hmm. During the summer season, it is easily the energy is easily provided by solar panels, so we don't have any problem. During the 6 months, we don't have any problem. During the winter season, we use small wind turbines. We use 4 wind turbines, each one of about 90 watts to generate the energy for the instrumentation and to send data to satellite. So despite the several problems we have during the winter, because it is a very low temperature with high winds, so the turbines suffer a lot, but we were able to maintain it during 10 years using the systems, and it operated quite well. So all our databases are available at the MetReader data from the British Antarctic Survey and Pangaea too. So all these 10 years databases are completely available there. But maintain that absolutely autonomous during the winter time, it's a big challenge here, in fact, during the winter. Yeah.
I imagine. Thank you.
Okay. Thank you, Heito. All right. No sign of Penny that I can see. All right, then. Okay, so let's see. Guy Athry, EM. I hope I pronounced your name correctly. Are you ready to present on the role of large-scale atmospheric forcing on short-term ice surface warming in coastal Dronning Maudland, East Antarctica? Yeah. So once again, you have 10 minutes. Please share your screen.
Yeah, am I audible?
Yeah.
Okay.
Okay. It just, yeah, great. Yeah. You're all set to go.
Okay. So hello everyone, my name is Gayatri EM. I'm a research student at National Center for Polar and Ocean Research. This work is part of my PhD. So the topic is role of large-scale atmospheric forcing on short-term ice surface warming in the coastal Dronning Maudland, East Antarctica. Surface melting over Antarctica has been a concern among the scientific world. So this is a satellite observation of annual surface melt from 2000 to 2009 from the continent. So here the surface melt is seen on the periphery of the continent. But in a global warming scenario, there is a high chance that this warming and melting events are increasing. So, and the mechanism of warming depends on a lot of factors like elevation, orography, and climatological conditions. For example, in Antarctic Peninsula, episodic foehn winds are causing more melting, whereas here in this part of West Antarctica, it is the warm moisture advection from frequent cyclones that are observed to be melting the surface more. And here it is the foehn wind from persistent katabatic winds that are causing more melting. Of course, this is not that much simple, and a region-wide study is required to understand the mechanisms happening in different parts of Antarctica. And also, there is inadequate knowledge on warming over the ice surface temperature. So, the aim of this work is to understand major warming mechanisms over the ice surface of coastal drowning mode land region for recent 5 years. The study area is coastal drowning mode land, and the data for surface temperature is obtained from borehole thermistors. So basically, borehole thermistors are deployed to measure temperature measurements from the cavity created from drilling of an ice core. So a set of thermistors are inserted in different depths from a height of 1.2 meters to a depth of 30 meters. So this can be a pictorial representation of borehole thermistors. And the location of borehole thermistors are marked as star in this figure, and it is at an elevation of 1,470 meters above sea level. The thermistors took regularly measurements from 2014 to 2018 in every 6 hours. So this is a field photograph of deployment of thermistors. So there are some short-term warming events recorded in the thermistors. So this is the time series of surface temperature obtained from the data. And here we can see seasonal changes with winter minimum and summer maximum. And along with that, there are some fluctuations, which are some continuous rise in temperatures for some degrees for some days. So we selected those events and examined them. So the selection criteria was of duration greater than 3 days and warming greater than 2 degrees Celsius. So with this criteria, we got 71 events. And then the general meteorological conditions during those warming events are like this. Out of the 71 events, 11 events were without any precipitation and 60 events were with precipitation. The surface wind pattern of the two are different. This is a surface wind pattern of events with precipitation. So here, this color bar represents the strength of the wind, and this represents the percentage of this particular wind direction. So for the events with precipitation, there is a maximum of easterly winds, and for events without precipitation, there is a maximum of south to southeasterly winds. So this two events we categorized as case 1 and case 2 and examined their mechanisms further. So these case 1 events occurred for most of the time, and it caused highest warming. To understand the mechanism of warming, we calculated net heat flux from as a sum of its components. So the net radiation and turbulent heat flux are obtained from ERA5, and ground heat flux is calculated from the thermistor data. We correlated the heat flux, net radiation, and turbulent flux to understand what is actually contributing to the net heat flux. So it was from the R values, it was net radiation that is mostly contributing to net heat flux. So net radiation is highly affected by cloud cover. So this is the histogram of cloud fraction over the location, and it was showing mostly cloud fraction of 1. So it is inferred that enhanced downward long wave radiation from clouds caused warming in the case 1. The upper level wind profiles of this case 1 events are like this. At 500 HPA, there is mostly northeasterly winds, and at 850 HPA, there is easterly winds. If we schematically represent the wind direction, it is something like this. At surface level, there is easterly winds. At 850 HPA level, there is prominent easterly winds, and at 500 HPA level, there is northeasterly winds. So these are all pointing to an idea that warm moisture advection is favoring cloud formation in this case, and that is causing the surface temperature to increase. As for the case 2 events, these occurred for least number of times and it has low warming extent. Here the correlation value is something different. The heat flux and turbulent heat flux are correlated more. So the surface, the 500 HPA wind pattern of this event was mostly southwesterlies, and at 850 HPA level it was easterlies. So the change in wind direction with height is like this. At surface level, there is stronger southeasterly winds, which is coming from the interior. And at 850 HPA level, there is easterly winds. And at 500 HPA level, there is southwesterly winds. So here, the warming is caused by strong turbulent heat flux from the vertical wind shear. So this is what we could identify for the case 2 events. Now, looking into the forcing mechanisms, this is the composite of mean sea level pressure anomaly for the case 1 events. The blue area represents low pressure, and high pressure is represented in red color. So for the case 1 events, that is event with precipitation, there is a passage of low pressure systems which directed warm moist air to the location. And for the case 2 events, there is high pressure over the location and low pressure over the west, both favored strong southeasterly winds over the location. So in a nutshell, there are two major mechanisms of surface warming in coastal rolling moorland region, both forced by large-scale synoptic circulation. The first one was surface easterly wind events with precipitation, and this is the major and more warming causing event. And the reason was strong downward long wave radiation from the clouds formed. And the top 20 warming events are in this category with maximum of 11 degrees Celsius warming over the surface. And there is a passage of low pressure systems during these events. And for the second case, which is surface southeasterly wind events without any precipitation, this is the least warming event and it has less occurrence. The reason was strong turbulent heat flux from the wind shear, and there is a high pressure system over the location coinciding with these events. So thank you for listening.
Okay, thank you. So I had a question for you. In your introductory remarks, you talked about katabatic winds and phones.
Yeah.
Is your case 2 related to that?
Actually, it is somewhat inland, somewhere inland than the katabatic zone. So, of course, there is katabatic wind effect, but it is lying in the ice sheet, this location.
Oh, I see. I see. Okay. So your warming events are driven by synoptic scale, mostly the cyclones, and
Yeah.
less frequently by the high pressure systems. I see.
Yeah. Yeah.
I see. Okay. All right. So any quick questions, other quick questions for our speaker? Okay, you can always type the questions in the Q&A and we'll have time for discussion, I think. Let's see. Okay, and okay, thanks very much. I don't see Penny. Okay, I'll give up on Penny, I think. And I guess the next speaker is going. Do we want to have a discussion of the papers, Adriana, or just carry on with the presentations?
Carry on with the presentations, and then we can discuss at the end all the questions that have arisen.
Okay.
Yes.
And maybe if we make a real point, yeah.
Yes.
Maybe if we make a real point of emphasizing people put the questions in the Q&A, that'll give us a basis for the discussion. Okay.
Yeah.
So the next presentation then is Gunther Heinemann. He has a recorded presentation. He's here to answer penetrating questions that arise. And his topic is Antarctic low-level jets during climate change. And 10 minutes, presumably on your recording, Gunther.
Yes. Hello, everybody. I will present some work on Antarctic low-level jets during climate change. We investigated using regional climate simulations, and most of the work was done by my PhD student, Rolf Zentek. So what are low-level jets? We consider low-level jets as wind maxima below 1,000 meters. We determine the height of the wind maximum, and we are searching for anomalies exceeding 2 meters per second, and using a maximum radius of 500 meters for the search, and search within 1.5 the maximum height. So we find this kind of maximum here in the lower troposphere. The model we are using is the CCLM regional climate model, which we adapted to polar regions. It is run with 15 kilometer resolution for the whole Antarctic. The domain is on the right. We implemented a sea ice model and did some adaptations for the stable boundary layer. We are using hourly data and 60 layers in the vertical with a high resolution of the boundary layer and the lowest level at 5 meters. The simulations of CCLM are nested into global simulations by the RV climate model, which consists of the atmospheric part ECAM6 and the sea ice ocean model FASOM. We see the FASOM model domain here, of course global. Both have a high resolution. Atmosphere is 100 kilometer, and FASOM, the color code shows you that there are 10 to 25 kilometer resolution in polar regions. The runs are performed for an historical period and 2 periods for future climate, mid and end of the century, all 15 years long. And we focus here in this talk on the SSP 370 run for the climate scenario. So first we go back to a hindcast study we did earlier with C15 nested in era interim and only for the Weddell Sea, which is published in this paper here. You see here the frequency of low-level jets, which occur very frequently over the slopes of the ice sheet here, more than 80 and more, sometimes more than 90% of the time. We found low-level jets here, and relatively low occurrences over the Filchner-Ronne ice shelf and the Weddell Sea area. This is the same picture but smaller. Now we compare this to the climate run for the historical period. If we switch forth and back, we see that we have a nice agreement for the katabatic wind regions and some slight difference over the ocean. But overall, it's quite good. We now look at the 3 time slices. start, mid, and end of the century, we see that especially here over the ocean area of the Weddell Sea, but also here in the eastern Antarctica, we find a decrease of low-level jets. So by eye, you cannot see much difference over the slopes where the katabatic winds are present. Before we go to differences, we look at verification. So that was the hindcast verification run for the Weddell Sea. And here we have a verification against the radiosonde of Neumayer, which is in black, which is here in the distribution diagram for the height bins. And we see the model simulation in blue and the radiosondes in black. They agree quite well. We have a slight underestimation of the model simulations. We go to the historical run, the climate one, then we see we have a slight overestimation by the model, but overall it fits quite well. So the model in the historical run is not far away from the hindcast run. Now let's look at the climate change signal, again for the low-level jet frequency. There we see from between the mid of the century and start of the century a slight increase over the plateau area and also in this area here and also over the Felchner-Ronne ice shelf, and decreases here over the sea ice areas of the Weddell Sea, but more for the eastern Antarctic here. The crosses mark points with a significant level. To the end of the century, the changes get much bigger, and we see that we have over most sea ice areas, we have a larger decrease here, more than 5%, and we have an increase, it's more pronounced than before, over the plateau area, and we see also a decrease in the katabatic wind areas. Apart from that, an increase over the Felchner-Ronne ice shelf. If we compare that with the distribution for the present climate, we see that where we have the increase over the plateau, the values, the present climate are rather low, but they will relatively increase very much. And we see that we have a decrease in the katabatic wind areas, which is in areas where we have a very high low-level jet frequency at the moment. Okay, summing up, I showed you the results of the regional climate simulations with 15 kilometer resolution for 3 15 years time slices, begin, mid, and end of the century. We find that the climatology of low-level jet frequency occurs or agrees very well with the hindcast run or the historical run. And the climate change signal shows that there is a decrease over ocean sea ice areas in general. There is a decrease in katabatic wind areas and an increase in low-level jet frequency over the Antarctic plateau. Some references about the model and methods. Most recent publication here of the hindcast run is published here, where you see also the methods and more diagrams. Thank you very much.
Okay. Okay, thank you, Gunther. So I wondered, do you have an explanation why you got the decrease in the coastal katabatic winds?
Yeah, I didn't show that. So when you look at the inversion, this slightly changes, get a little bit weaker. But I think most of the changes are given by the different synoptic forcing on the katabatic wind.
Okay. Do you think the synoptic conditions are well captured, you know, in terms of location and intensity, you know, persistent changes from the climate models?
I didn't check that, but at least you saw for the statistics of the katabatic winds, it looks quite good.
Uh-huh. Yeah, it's, you know, how well they respond to the remote forcing, and do they put them in the right place at the right intensity? That's okay. That's something for the future, but just as a general observation. Okay. All right. And all right. So once again, everybody put your questions in the Q&A, type them out, and we'll have a more extended discussion at the end. Okay, so the next presentation is Tamara Pletzer, talking about modeling the hydrological connectivity of glacial meltwater during a phone event in the McMurdo Dry Valleys. And Tamara, you have 10 minutes. Please share your screen.
Okay, can you see my screen?
Yes, we do. It just needs to be in presentation mode.
Sweet. Awesome. Hi, I'm Tamara Pletzer, and I'm a PhD student at University of Otago in New Zealand. I'm supervised by Marwan Katurji, Nicholas Cullen, and John Conway. Today, I'm going to be talking to you about a proof of concept research project that's been working on modeling the hydrological connectivity of glacial meltwater during a firm wind event in the McMurdo Dry Valleys. So, as you might have heard in some other presentations, the McMurdo Dry Valleys are a unique ecosystem of cyanobacteria that is dependent on solar radiation and fresh water. So this project is contributing to research priority 3 of the Antarctic Science Platform, which hypothesized that in a warming world, there will be changes to the distribution of fresh water, and this will have downstream impacts on this ecosystem. So air temperatures in the summer are currently around 0 degrees, which can result in highly dynamic transitions between water and ice, as well as water vapor. And fresh water is mainly found in a system of lakes and streams in these valleys. Firm wind events have been identified on the Antarctic Peninsula, among other areas, as a driver for extreme warming in this region. And then previous studies have mainly implemented, previous studies have mainly been focused on implementing a surface energy balance model in order to estimate the quantity of melt and also the amount of energy available for melt. So this study is kind of resolving that gap for resolving spatial distribution of stream flow. So the aim of this research is a proof of concept to model the hydrological connectivity of glacial meltwater. The objectives are to implement a hydrometeorological modeling system framework in order to assess the meltwater generation and transport. And also the second objective is to test the modeling system using observations from strain gauges as well as automatic weather stations. So here's a little bit about the modeling framework that I chose to use. So it's called WRF Hydro, and it sort of is linking a few different models rather than just being a model itself. So you put in input static data. So this will be things like a digital elevation model, but also mapping the different streams. And similarly, static data like land surface classifications that is used by WRF models. And then there's also dynamic data. So this is the atmospheric forcing data. And for this one, I chose the AMPS model, and I used the 0.89 kilometer domain over the dry valleys, and then downscaled that to the size of my land surface model. So the land surface model is the default here, which is the NOAA MP model, and that was run at 200 meters. And then it was coupled with a terrain routing model, which was at 8-meter resolution. And then there's also channel and reservoir routing modules within that. So there's a lot of regridding happening within this framework rather than just being one model. So for this case study, I chose the summer of 2018-2019 and first plotted some air temperatures from the automatic weather stations and then compared it to stream gauge data and identified this as sort of an area of interest. So there is a large spike in stream flow, and there's also some of the highest air temperatures that are seen during this summer. So in order to verify whether it was a Fern event, I looked at AMPS data, and here I plotted potential temperature lines through Taylor Valley, which is this cross section here. So this side up here is the left side of all the plots below and to the side, and then the McMurdo Sound over here is sort of the right side of these plots. And in the first time period, we have, this is sort of like a typical setup during the summer. So you have a cold pool down in the valley, and then aloft you have your warmer potential temperature lines and a bit of an inversion happening, and it's quite stable. And then as we move forward through time, we have this plot down here, and we can see that there's some interesting things happening aloft. There's probably some turbulence coming in, and we have some warmer potential temperature lines. And then over deeper in the valley and towards the sound, we still have that cold pool that's persisting and the inversion. And if we fast forward another 24 hours, you can see that there's quite a lot of warmer potential temperature lines that are being drawn down all the way to the valley floor. So that's kind of a good Fern signature right there. And then if we compare, now we can compare some like the input data, which is the atmospheric data from AMPS that was regridded down to 200 meters from 890 meters. And this above we have AMPS, and then below we have different automatic weather stations. And in terms of incoming solar radiation, AMPS is a lot smoother than what you see happening in real life. And also never quite reaches as low values as you can see in the observations, which is likely due to shading effects. So in that sense, AMPS doesn't perform super well. But if we look at a different field, such as air temperature, we can see that with root mean squared error of 2.59 and a bias of negative 0.79, AMPS is performing quite well. And you can see that it's matching a lot closer to what's happening in real life. So here's some preliminary results from the hydro model. So here are some hydrographs. This is from, the first one's from Canada Stream, which is in Taylor Valley. And here we can see that the model is really capturing this diurnal variation, but sort of misses the major events. So observed here is the dashed lines, and modeled is the bold line. On the other hand, here's a plot from the Onyx River, which is over in Wright Valley, just one valley up to the north. And we've got two stations here. So in black, we have the Lake Vanda station or stream gauge, and in gray, we have the lower right. So the river flows from the lower right station down to the Vanda station in terms of timescales. But here you can see that the model's capturing the general shape of what's happening. It's obviously a lot smoother, but it does actually miss the timing of the peak. It's a little bit too late, but here it does capture the exponential decay of the Lake Vanda station. So some more preliminary results. Here's spatial distribution of stream flow.
2 minutes.
So over here we have Taylor Valley, and here we have Wright Valley. And I'll just play this video. So this is a good example of why we're interested in the system. So daily, there's some kind of variations in stream flow, but ultimately it's these big events that light up the system and result in lots of stream flow. Just a quick note that the Onyx River flows downstream in this direction, whereas the streams in Taylor Valley do flow towards McMurdo Sound. Sorry, I've replayed that. Oh. Okay, so that's just a proof of concept. So the model is performing relatively well in its first implementation without many tweakings. This is mainly in the default mode. So what's next is mainly, there's a newer version where the snowpack model Crocus has been implemented over glaciers instead of NOAA-MP. And this is quite interesting because Crocus is a physically based snowpack model, and that kind of gives us a lot more options in terms of looking into the mass balance and energy balance of the snowpack, whereas NOAA-MP's a 3-layer model, and once those 3 layers melt out, you just are left with a bare ice land surface category that can't decrease in mass or extent. So that's kind of the next iteration of this, is implementing this model and then being able to compare it to the NOAA-MP version. But yeah, thank you for listening, and any questions?
Tamara, I wanted to ask you briefly. So the Dry Valley is a very challenging environment because it's these, in these mountain ranges with these deep valleys there. So it probably is true that 900 meters for grid resolution is probably not nearly accurate enough to capture, everything going on in the dry valleys. I mean, AMPS is there every day, 2 runs a day, so that's very good. But when you said you downscaled it, how did you do that?
Yeah, very good question. So for the downscaling, I just used like a really simple bilinear regridding scheme. It wasn't very fancy. I think I agree that the 900 meters is pretty coarse for the dry valleys, and I guess that's something that I'm exploring in the newer iterations of the model, is trying to figure out if it's kind of where the largest sources of uncertainty are, because there's a lot of parameters in the model as well that I can tweak, but also a large source of uncertainty can be the input data. So yeah, I'm still kind of figuring out whether it's worth me looking into the input data more and doing either a statistical scaling or something more sophisticated rather than just like a bilinear regridding.
Okay. I mean, you could consider, you probably don't want to do this, but you could actually consider running WRF nested within AMPS. That's probably more than you want to do, but that might be a way of really optimizing the resolution. But then that's considerably more work than a statistical downscaler, for example.
Yeah, no, that's definitely an option. I have been working with someone at Vic who is running Polar WRF, but she's at a way coarser resolution right now. So I think we were always thinking that if she moved to a higher resolution, I could use her input data, but until that happens, I'm probably just going to stick with this. We'll see how much time this PhD has, but you're right, that would probably be the best possible option.
Yeah, ideal world. All right.
Definitely.
Okay. All right. So once again, thanks very much, Tamara. So Marta Hofsteinge, I hope I got the name right.
Hi.
And more about phone events. This is on the impact of phone events on the energy balance of Joyce Glacier, McMurdo Dry Valleys in Antarctica. Okay, so once again, you have 10 minutes. Please put your presentation in presentation mode. Thank you, and we're all set to go.
Okay, thank you. Hi everyone, I'm Marta Hofsteinge and I'm as well a PhD student at the University of Otago in Dunedin. And I will be telling you today about the impact of phone events on the energy balance of the Joyce Glacier, which is also located in the McMurdo Dry Valley. So same region as Tam has been telling about. We're part of the same project, which is funded by the Antarctic Science Platform, which focuses on the impact or the changes that might occur in the terrestrial habitats in the Ross Sea region, which is mainly the dry valleys, since there we find these lakes and streams that are habitats for life. And we really look at what are the climate effects on these ecosystems, and that really goes through meltwater. So we want to understand what drives meltwater generation in the dry valleys, and our hypothesis that it's mainly linked to episodic warming events. And today I will be telling more about phone events and how they might impact the melt of the glaciers in the dry valleys. And I do this specifically with a study on the Joyce Glacier. So the Joyce Glacier is located over here in the southeastern part of the McMurdo Dry Valleys and the Ross Sea region, as you can see here. So it's a bit more, on the southeastern side of the Royal Society Range right here. So Tam was talking about Taylor Valley, a bit more northern right here. So for your orientation. And I used in the study a 14-month observational record of weather station observations. And those observations we can use to run a surface energy balance model. So with this model, we calculate from our observations how much, how large the energy fluxes are and how much energy there is available for melt. I also use the observations of temperature, relative humidity, and wind speed to detect the typical phone conditions at the Joyce Glacier. And I also use the Antarctic Mesoscale Prediction System output, so AMS, where Tam also talked about, to look into more detail in the meteorology of these phone events. So this is the equation that's solved to calculate the energy balance. So what you see is QM, which is an amount of energy available for melt, which can be calculated from a balance of the radiation terms, so shortwave and longwave radiation, a part of this shortwave radiation that goes into the subsurface, so that's the QP, so that penetrates into the subsurface and heats the lower layers of the ice, a conductive heat flux, and the turbulent fluxes. So they make up how much energy there is available for melt. And how it looks over a full year is what you can see over here. So you see quite clearly a large net solar radiation flux here in orange, which is really the main flux in the energy balance of the Joyce Glacier. And we see that there is a strong loss of energy through net long-wave radiated cooling. In summer, you see also here in light blue that there's quite some energy used for sublimation through the latent heat flux. And quite remarkable is that you see in black just a little residual, which is this energy that's available for melts. So that's very typical for the dry valleys. We have large fluxes, but overall the residual that is left for melt is small. And we also see that the melt is strongly radiation driven. So we see that the peaks in melt are actually when only the melt occurs, is when solar radiation peaks. And that's often in cloudless conditions or when the albedo is lowered. So I've already mentioned that we're going to look at some föhn events. So when do föhn events actually occur in the dry valleys? So they occur when there's anomalously low pressure over the Rossy region. So you can see here, this is a composite of the sea level pressure during föhn events of the Joyce Glacier. And this anomalous low pressure indicates that there are cyclones present over the Rossy region. And they will lead that there will be a southerly flow towards the dry valleys. And when the southerly flow hits the dry valleys, the lower levels in the atmosphere will be blocked by the Royal Society range, so by this mountain range. And as you can see, a part will go on the left of these mountains and a part will go deviate on the right. And the part that goes in the left, that leads to a gap flow and a typical föhn signature that Tam showed before in the more northern valleys, so Taylor Valley and Wright Valley. And on the right side, probably the same. But there's also a part, so the lower part gets blocked and goes around the mountain, but the higher levels in the atmosphere can pass over the mountain. And during these föhn events, this potentially warmer and drier air from aloft can get drawn down towards the surface. And that's what we see here at Joyce Glacier. So Joyce Glacier is just located here on the east side of this mountain range and is really experiencing föhn conditions because of this isentropic drawdown mechanism. So this shows again also, as David Bromwich said before, that the dry valleys are indeed a very complex system, and also the föhn mechanism really varies on a small spatial scale. So in one location it can be gap flow and mountain wave driven, while in this location it's driven by isentropic drawdown. And then I can use the output from my energy balance model to actually look how these föhn events impact the energy balance. So here we see in the figure in the top the energy balance terms, and in blue you see the shading. In the blue shading you see when a föhn event occurs, and in the bottom we see the ablation terms, so surface, internal melt, and sublimation. And what we see that during föhn events there's often stronger sublimation. So because of this windy and dry conditions, there is a lot of energy used for sublimation, and we see that there's a switch in the sign of the sensible heat flux. So often it's actually pretty unstable, so the surface is warmer compared to the atmosphere above, but during föhn, the warm atmosphere really is an extra source of energy to the surface. And we also find that föhn only occurs about 6% of the time in summer, but it contributes to 90% of the total melt. So at least for these 2 summers at Joyce Glacier. So we find a relatively larger contribution to melt during föhn events compared to normal conditions. And this is because in summer, the surface temperature is actually not always at the melting point, and föhn events can really provide this extra energy, this push to reach the melting point, so that melt actually can occur. We also found that that melt rates are slightly higher because of an albedo effect. Also, something interesting was that we didn't find the impact of the föhn on clouds, at least no clear trends in this 14-month data set. But we will look more into that, since this is actually found on the Antarctic Peninsula, but it might work different in the dry valleys. So that's something for future studies. And if we then look at the same things, but more on a diurnal time scale, you see that under normal conditions, we see a typical diurnal cycle here in the temperatures in orange and the air temperature, and a diurnal regime in the winds. So during the night, we have drainage flows down the glaciers, and during the day, we have winds coming from the sea. And this gets replaced during föhn by wind direction from one direction, which is this typical föhn direction. The winds are strong and the air temperature is much higher. So if we then look at the energy balance terms, we see mainly that there is a switch in this sensible heat flux. So it's always an extra input of energy, but it's largely compensated by extra heat energy that will be used for sublimation, which is shown here in blue. And we see that overall in black, that's the residual again, the amount of energy that's available for melt. And we see that it's slightly higher during föhn conditions, which is because of a slightly lower albedo. But I have to note that it's just a few föhn events in these 2 summers. So this is something that we want to confirm with a future study where we can really look at several years at different glaciers to really confirm this, the role that föhn has on the energy balance. We already have some new observations from last seasons with eddy covariance data. So that's great to confirm the stability regime that we found. And we saw, again, this is for a different glacier, for Commonwealth Glacier, but we see the same pattern of a diurnal cycle in the wind direction. You can see here on the y-axis, and also a diurnal cycle in the surface stability. So you see that it switches from a negative to a positive sensible heat flux. And then if a föhn event sets on, it's again here in the blue shading, we see that the wind direction is suddenly very different and there's much stronger sensible heating. So that's really this windy, warm föhn air. So you can imagine that that gives an extra energy input to the glacier. So in conclusion, we found that föhn warming mechanisms vary spatially in the complex topography of the McMurdo Dry valleys. We found that the melt was mainly driven by solar radiation, but that föhn increased the melt occurrence and also the melt rates. But since this was only based on a 14-month period, we would like to confirm this impact of föhn on the energy balance by looking at several glaciers and over a longer time period. So I'm working on that at the moment. And we also want to look more into the role of clouds. We can imagine that some glaciers will be closer to the coast and more influenced by humidity coming in from the coast. And I want to study how this föhn might erode the clouds or how it goes together. You can imagine that the melt is solar radiation driven, so cloud cover can really impact the melt or the effect of föhn on the melt in the dry valleys. Thank you for listening. If you want to learn more, please contact me or follow me on Twitter. And you can also find the preprints of the Joyce study on the cryosphere online. So I'm happy to hear any comments or questions. Thank you very much.
Okay. Okay. So Marta, I wanted to ask you about calculating the various terms in the surface energy balance.
Yeah.
So did you, you took those from the automatic weather station observations? Is that what you did?
Yeah, so we have observed solar radiation, so incoming and outgoing. So we have a record of the albedo. We have incoming and incoming long wave radiation, and the model calculates the surface temperature. So that's the outgoing long wave radiation is modeled. And then the sensible heat fluxes and the turbulent heat flux are calculated using a bulk method. So using the gradient between the weather station and the surface. So the surface temperature or the saturation at the surface of the ice.
I see.
And also the wind speed, of course. Yeah.
Yeah. Okay. And the ground heat flux, that QG term, where does that come from?
So a part of the solar radiation, of the net solar radiation, so the part that's not reflected, that still goes into the subsurface and it dies out with the layers. So this heat gets released, and a part of that heat conducts back to the surface again if the surface is colder, or it can actually heat the ice back, depending on if the atmosphere is warmer compared to the ice layers or not. So that's QG. So that's the conductive heat flux. So it depends on the temperature gradients between the layers in the ice pack or snowpack.
And is that measured, the temperature profile in the ice or snow, or is that?
So at Joyce Glacier, we had some observations, but it's quite hard to do these observations because sometimes the sensors are dark, so they actually absorb themselves too much radiation. But I'm working now at Commonwealth Glacier, and we had better observations there. So then I'm using indeed these observations to validate if the amount of energy that goes into the subsurface of the glacier, if that is of the right order of magnitude. Yeah.
Okay. Okay. All right.
So it's more for evaluation or validation of the model. Yeah.
Okay. Okay. Great. Okay. Okay. So once again, any questions, please type them into the Q&A, and we'll go back in the discussion after the next presentation. Thank you, Marta. So the next presentation is Ava, all right. Ava Nielsen, I think. Yep, okay.
Yes.
Once again, back to the McMurdo Dry Valleys, back to foam warming, and a case study from a new continental scale air temperature data set, ANT-AIR version 2. Okay, once again, you have 10 minutes. Please share your screen and just put it in presentation mode. That's great. And you're all set to go.
Yes, thank you so much. And thank you for letting me present here today. My name is Eva Nielsen, and I'm a PhD student at the University of Canterbury here in New Zealand. And yeah, absolutely right. I'm going to talk about this new temperature data set I have created called ANT-AIR and its relation to how it can be used in food warming detection. Yes, and I'm also a PhD student under the Antarctic Science platform. So you're going to hear a little bit more about food in the dry valleys. Yes, so what I'm really interested in is mesoscale climate variability, and especially temperature variability on the hourly to daily temporal resolution. And underneath this mesoscale variability and temperatures, we have the food warming events. And we know that Antarctica is, as we say in our research group, the land of food, because we have this steep coastal terrain and we have the synoptic scale low pressure system that are circling around Antarctica, creating the ideal conditions for food warming happening along the coastline. This is also shown in previous studies. We've also been talking quite a lot about food in this session today, but just to take some examples, we have quite a lot of study from the Antarctic Peninsula, the dry valleys. There are a few studies for the Ross Ice Shelf and Emery Ice Shelf. So studying these foods, as we also talked about today already, is you can identify them using automatic weather station and different classification algorithm in automatic weather station. However, due to the really remote location of Antarctica, these automatic weather stations are not very densely spaced. Another solution, which is quite common and really helpful, is using the Antarctic mesoscale prediction systems, as we already saw today in some of the previous presentations. However, AMPS is only available at a really high resolution that are good enough at resolving these intervalley variability within the dry valleys and the Antarctic Peninsula. If we go to a more continental scale data set, we have the reanalysis data from ERA 5. However, we have a resolution that is so low that we're not able to detect these intervalley variabilities. So what I thought we were lacking through all of this is some sort of temperature data set on a high grid resolution that are available for full Antarctica for a long time period and able to identify certain locations of interest. And therefore I come up with this temperature data set that I call ANT-AIR version 2. Version 2 is because my supervisor Hannah Meyer did a version 1 back in 2016, but we have made an updated version, which I'll talk about in a next session how we came to that. But this temperature data set is available at a 1 kilometer grid resolution for the entire Antarctica for the past 19 years. And I'll use this data set as a part of a data-driven approach along with the other data set that I just listed for identifying food warming along the coastal threshold margin of Antarctica. Yes, so ANT-AIR is what we have defined as a near surface air temperature data set. It is based on the remotely sensed MODIS land and ice surface temperature. So the MODIS is an instrument attached to the Aqua and Terra satellite that do a polar orbit around the Earth and thereby provide daily and nightly land and ice surface temperature. There are previous studies linking how the MODIS land surface temperature are related to automatic temperature measured in automatic weather stations. And I therefore gathered weather station information from 140 different weather stations. You can see on the map up here on the right. I'll also like to say thank you for everybody who has contributed to this data set. And I thereby found a linear regression that fitted this relationship between the temperature measured in a weather station and the MODIS land surface cell. Once we defined this model, I then applied it for the full MODIS data set or product. So we therefore have this temperature data set that available in a 1 kilometer grid resolution from 2003 onto 2021 in a daily mean temporal resolution. If we want to look at how well Ant-Air is performing, I did a temporal validation. So I extracted every third year from this data set that I didn't use for my regression, but then used for a temporal validation. And as you can see, we have RMSE around 3 degrees and a mean absolute error around 2 to 3 degrees. The ice surface temperature model is performing a little bit less precise than the land surface temperature, which is due to some inconsistency in the MODIS ice surface temperature product. We also see a little bit of variation in how well it's performing on the different seasons, where December, January, February comes up as the season where we have the highest accuracy for this. In order to estimate or try and compare this to other available data set, I extracted the ERA 5 temperatures for the grid cell for these 140 weather stations from the same period as I did my temporal validation. I did a dry adiabatic lapse rate correction in order to correct for the topography. Yes, and then I did the same mean absolute error and RMSE for the daily mean.
May I have your attention, please? This is a test
of
the talkaphone
yes.
evacuation
Sorry.
system.
Repeat,
this is only
I don't know. Can you hear this? Oh, sorry, I'm in the room and apparently there was an emergency. Sorry about that. I'll continue my presentation. Yes. Yes, so as you can see, the ERA 5 have a little bit higher RMSE and mean absolute error than Ant-Air, which is quite promising. Yes, so I'm hoping to use this Ant-Air data set for investigating these mesoscale climate variabilities. And one of the variabilities that I'm really interested in is these föhn events, as we already talked about quite a lot today. And I found this föhn event and hopefully convince you guys that Ant-Air can be used for föhn warming detection. So it was a weather föhn event measured in the Lake Bonny automatic weather station here in the Taylor Valley that are within the dry valleys in the Ross Sea region. We have this low pressure system here and the high pressure system inland that are causing the flow over the gap, as Marta explained previously, and are then causing channeling through the Taylor Valley. And as we can see in the potential temperature here, it's diving into the valley. And yeah, if we then investigate how the weather station is illustrating this föhn event, we see a clear change in temperature a clear change in wind direction, which are leading to a drop in relative humidity and increase in wind speed. And we can also see that the temperature for this 5-day period that are classified as föhn warming, if we use the Spears classification algorithm, yes, so we have these, we can see that the diurnal circle is still present in the air temperature, but overall we have above 0 degree for this full 5-day period, which is quite interesting and is possible for then creating these potential melt events as we also talked about tonight. So now that I established that it's a föhn warming event from other sources, I wanted to show you how Ant-Air is solving these föhn events. So I'm comparing it to AMS domain 3 for the 1st of January and the 3rd of January 2014, where we have this event happening. You can see from the AMS domain 3 that it shows that the wind are being channeled through these the dry valleys, and we see that the temperature in the dry valleys are higher than the surrounding area. However, when we look at Ant-Air, we see a higher temperature trends down here in the dry valley. So the star is where the Bonny automatic weather station is located. and we see how the temperature increase as we move to the 3rd of January. I was quite interested in investigating why we had this difference in the temperature. So I looked at the daily mean for a 20-day period around this temperature. And we have the automatic weather station, the ANDAIR, and the AMPS data here. And it seems like the AMPS has a cold bias for this weather station, or for the location of this weather station, and is therefore predicting below 0 temperature, whereas the automatic weather station and ANDAIR are having this continuous above 0 temperature. Yeah, which was quite interesting. So hopefully with this, I have illustrated that ANDAIR can resolve these food warming event due to its high grid resolution. So I wanted to take a step back because now we have shown how ANDAIR and the high resolution are capable of showing these food events that are causing above 0 degrees temperatures. I therefore created this small animation to illustrate which region of Antarctica that ANDAIR picks up as having temperatures above 0 for certain days. And you can see here how different regions from different time periods are experiencing these above 0 temperature. So I have the full period from 2003 until 2021. Yes. So we are, so these are going to be our regions of interest, because for instance, if you zoom into the Ross Sea region that we have here, so we have the Taylor Valley, we can see how the valleys are showing these above 0 temperatures. It seemed like ANDAIR is overestimating the amount of days that have above 0 temperatures. But in general, we are able to classify these areas that experience extreme temperatures. I am more than well aware that a lot of these will not be food warming events, but it will give us an indication of dates to look at and then connect to larger scale circulation and then identify what are perhaps causing a lot of these events. So in summary, Antarctica, the land of food, but where are these food events outside the already known location? I have designed ANDAIR Vision 2, which provide a high resolution Antarctic-wide near surface air temperature. We know that the fin warming signature are visible in these ANDAIR, but however, since ANDAIR is not showing relative humidity, wind speed, we still need other data sets to give us these information. So ANDAIR will be part of this data-driven approach to identify areas of interest and thereby further investigation if those can be related to fin warming events. So thank you so much for listening in. And yeah, if you have any questions, feel free to ask.
Okay. Thank you, Ava.
Yes,
right,
and sorry for the interruption. It's not.
Yeah, that's always the way it goes, right? Okay, all right. So any questions for Ava first before we open it up for more general discussion? Okay. All right. So I actually have a question for Ava and Gunther Heinemann. Gunther, didn't you construct a similar kind of data set to what Ava is showing? Didn't you use MODIS land surface temperatures?
Yeah, I just sent her a mail with an article we published.
Yes, thank you.
Good. Well, then I don't have to have an answer to that question. All right. And Marta, did you just do this for the summer, or is this, oh, you did it year round, didn't you?
Yeah, it was for a 40 months period. So from the beginning of one melt season until like the whole winter and to the end of the next melt season.
Yeah. Okay.
Yeah. And at the moment, I'm looking like trying to compose a 20 years series for 2 other glaciers. Yeah, to study more the temporal variability and be able to get more trends.
Okay. All right. Okay, so yes, I mean, so there was, you know, my research group was involved in some of the early work with the phones in the dry valleys with Johanna Spears, and it does seem like phones are being detected everywhere, basically in Antarctica. So it's happening in a lot of places. I'm sure we don't know most of the locations it's happening. So Ava, maybe your data set is the clues to unearthing this.
Yeah, that's really what we were hoping. It's my supervisor Payments. He always called it Antarctica, the land of Föhn, because he seemed like there is the ideal conditions for generating these Föhn wind events. And I was quite happy listening to the talks earlier today, where a lot of people were mentioning Föhn. So yeah, we definitely hope to identify some other regions that might be experiencing some extreme temperatures linked to Föhn warming. So yeah, it's quite exciting.
And of course, you know about these extremes in the peninsula area, which are, you know, contributed by anyway, several of the stations there. That seems to be breaking these temperature records quite frequently, apparently.
Yes, for sure. I think for my case, seems like the Antarctic Peninsula is already studied by a lot of people, and there's a lot of research already happening there. So I think my approach would be to find regions that are less studied. But yeah, there are definitely some cool things happening in that region as well that can inspire us.
Absolutely. And my former PhD student, Jerry Zhu, was studying the Föhn events on the eastern side of the Ross Ice Shelf, you know, in Mary Bird Land, for example. And so, yes, there's interesting happening in a lot of places. So I noticed in your animation that, you know, because we were studying the big events, and it's happening every few years, and it seems like 2016 January was a big El Nino year, and I think it showed up in the animation that you showed. It kind of lights up, you know, extending well into the interior of Mary Bird Land, but it's quite episodic.
Yeah, we do have one issue with the MODIS, that when there's a cloud cover, it blocks for the MODIS information. So once there's cloud cover associated with Föhn, we're not able to detect it. And for some of those events, unfortunately, there was cloud covers, because we tried to look into recent literature for Föhn wind events outside and then see how it was comparable. Unfortunately, the cloud cover set a little bit of limit to some of those. So that's definitely one of the drawdowns of this project.
Okay, yeah. Okay. All right. Thank you, Ava. So, all right. So this is the time to have, yes, Gunther.
Yeah, I have a question, a remark to Gayatri. Are you there?
Yeah.
Okay, a question would be, you're using a thermistor chain for measuring air temperature, and I guess it is not, has no radiation shield, is not ventilated. So there may be big errors for the air temperature. And the remark is, so you said you have a Föhn event in the katabatic wind. I think for the Föhn event, you need the mountain before in the flow, but for katabatic wind, you may have the warming due to the mixing of the surface layer. The wind is strong. So you should also look at the wind speed associated with the warming.
Yeah. Okay, and I have measured the ice surface temperature, not the air temperature, from the thermistor data.
Yeah, but the ice surface temperature with the thermistor, this one gets a lot of radiation, and the values are not correct.
All right. Okay. All right. So let's see. Any more questions for our speakers? I certainly have. Well, I can generate a lot of questions if nobody else is. Maybe I can ask Sergey.
Yes, tell me.
All right, so this 2020 warming event, how certain are you that it's climate change? What are the, in other words, you presented the arguments, but we all know that there's weaknesses in every argument. So let me ask you what you think the limitations to your analysis is.
Of course, there are, okay, our analysis have some limitations. And indeed, in the paper, we indeed ask to do another kind of analysis because there are, okay, in attribution studies that have been very popular in the last years, there are two main schools of attribution. One is from modeling, and the other one is from analogous studies. Indeed, modeling studies are the most popular and maybe the most robust studies of attribution, but they may have limitations if the modeling itself is not able to reproduce well this kind of events. But they are the most popular analysis right now. Analogs studies is like the poor attribution studies, but also have some, they have weaknesses if the data, if you don't have a long data set, for example. I did the study previously to the release of the era 5, of the first years of the era 5. You know that first was released the era 5 from 1979 to today. But and I did the analysis with that, and I didn't have the conclusive analysis because the time period was very short, and I wasn't able to reproduce again the study until I had the data set from 1950. This is one of the main weaknesses, but I think that we with this data set we overcome that weaknesses. And the other ones is if the analogs itself reproduce the analogs. So to overcome that, what I did is to do a lot of sensitivity analysis. I changed a lot of things. I maybe did the same analysis 50 times, changing small things. For example, the regions. I changed the different definitions that I used, and all these changes led us to the same conclusion. So I think it's quite robust, but it's not perfect exactly.
Okay, so one observation that can be made is that, you know, in recent years, at least the summer temperatures in the peninsula in general have been decreasing.
Yes.
So how do you think the averages and the extremes fit together?
Okay, it's a tough question.
Sorry about that.
No, it's a very interesting question. Yes, it was this hiatus, that occurred from 1998, I think, to 2016. And now it's increasing again, I think. But even that, even it was a decrease. It was a decrease from a very high temperature. So if you compare the temperature, the mean temperatures in the second half of the data set, is even with this decrease higher than in the first half of the data set. But you ask how this affects to the increases. I am not sure. I think that you have like a baseline of temperature, and when you have, for example, in this case, an foreign event that we are talking a lot about foreign Antarctica, the land of foreign, you have a large increase from this baseline. If you go up the baseline, then the foreigns will increase even more the temperature. Well, the increase is the same, but you start from a baseline, from an upper baseline. So I think this can be the mechanism, but it may be better studied than only this hypothesis.
Okay.
So Mario, also a remark to that, you selected the time period before and after 1985. So the
Yes.
warming is known to have, but the cooling has began at around 2000. So you may select 2000 year as different periods.
What we did is to split with the same with periods of the same time scale, 35 years or 35 years. That's why we split in 1985. But the question is, it's in general no. In the second half of the data set, are the situations analog to this situation, to the 2020 situation, are warmer than in the past. So you have head wave events, reproduced head wave events, using years from 1985 to 2020, but you combine them randomly, you achieve to have, okay, I don't know how to say it. Okay, I think that as you reproduce 5,000 analogs, you achieve to have a less error than picking exactly, than changing the time of the data set. But I even tried to change the years and other things, and also I did a lot of sensitivity analysis, and always led us to the same conclusions.
One more question. So your analog situations were very few, something like 10 for each period. Have you looked at extreme value statistics, looking at thresholds? So if that had changes, or if only the extreme gets more, has been more.
We didn't do extreme event values analysis. We did this kind of analysis only, but so we did not look if the extremes are becoming more extremes or not. So I cannot answer this.
plenty of work for the future. I think that's the long and the short of this. And we might wait, and Mother Nature will deliver some further extremes for us to study. Maybe that'll be the deciding answer to all of this.
Yes.
All right. So more questions for our speakers. All right. So let's see. Maybe I can ask phone warming. I don't know who to ask this question of, but there are 3 presenters on phone warming in the general area of the McMurdo Dry Valleys. But there are these big events, right? Really big events where, basically you get almost flooding in some summers in the valleys. The automatic weather stations in the dry valleys haven't been going that long, have they? It's this lawn array, I think. So we don't have in situ observations for that long in the dry valleys in general. I think that's true. So how well do we know the frequency of these big events and their attribution? Is there anybody that is familiar with that kind of work in the dry valleys?
I think the longest record for one station is it's about 30 years, I think. I'm now trying to compose a series of energy balance and also phone occurrence for about 20 years. Like most stations have about 20-25 years. But for sure, there's some gaps in the different weather stations. But I think the longest record is about 30 years. So we have some kind of idea of the variability from year to year in phone events and also in melt. So it's true, like I think in that period, like 2001 and 2011 were 2 clear years with a lot of melt, while some years almost don't have any melt at all. Yeah, so that's a bit the data we have on variability there.
I seem to remember that there was a big iceberg in one of those years in the Ross Sea. It broke off from the Ross Ice Shelf, and there was some question, maybe it was the early 2000 event, and some people were wondering whether there was a connection between the big iceberg sitting there and what was going on in the dry valleys.
Okay, that's interesting. I never heard about this. Yeah, I'm interested myself to see if there's any link with sea ice conditions as well, because I think clouds can be quite important in driving, or not driving, but avoiding melt. Like I think if there's too much cloud cover, melt will not occur because it's so much solar radiation driven. So it might have to do with just, yeah, what's temperatures of the ocean, how much sea ice there is, maybe also icebergs. Yeah, I'm curious to see. I will have a look at that year.
Yeah, that was a really big iceberg.
Okay.
So in a lot of these valleys, maybe Taylor Valley or Wright Valley, there's this diurnal cycle where the air comes in from the sound. And then there's the outflow at night, I think. So it's this interchange, and I guess it's the lower part of the valleys where this happens. So is it kind of a sea breeze type circulation so a sea breeze, land breeze circulation that happens?
Yeah, so during the day you get winds from the coast, so coming from the east, and during the night you see this typical down glacier winds, or the down valley, mostly down the glacier. Yeah.
Okay.
Yeah.
Okay.
And it also gives this, what I showed, the regime, like this diurnal cycle in your stability, or like the very surface layer stability, like just above the glacier.
Okay. So if the cloud and the moisture comes in from the sound, you're not going to get, as you're saying, you're not going to get any melting going on in the region where you're getting that advection.
Yeah.
And okay.
So yeah, right now I'm, for example, looking at also the duration of föhn. So I'm comparing Commonwealth, which is very close to the coast, with Taylor Glacier, which is more higher up in the valley. And you see that in the weather station observations, you see this föhn event going on for much longer at Taylor Valley compared to Commonwealth, because it will be interrupted again by this sea breeze circulation. So you see that the humidity goes up again because this sea breeze picks up. While at Taylor, which is a bit higher up in the valley, you see that actually can be for days that you see this windy and dry conditions.
Okay, I see. Okay.
And also it's still like pretty dry as well. So like even the cloud coming in off the ocean, like I spent like January and some of February in the dry valleys earlier this year. And it looked like once the sea ice broke out, we were in Taylor Valley mostly. Once the sea ice broke out, you'd get like your sea breeze and you'd get like a little line of stratocumulus that would just like march up towards Commonwealth Glacier. But it's so localized that, you know, Canada Glacier right next door is not experiencing that low level cloud, and not even all of Commonwealth is experiencing it. So there could still be melt around it on the same glacier.
Okay.
But that was just personal observation. I'm sure there's other observations that other people have made too.
Okay. Interesting. Okay, so more questions for our speakers here. All right. Maybe I can ask, since nobody else has any questions, apparently, I'll ask Heitor if he's still here.
Hello?
Yes.
Yeah. So I was having a look while you were talking, and that big warming event that you talked about, that 30-degree warming event, that was just outside one of our special observing period, targeted observing periods. It just happened about 3 days later than that ended. So it was interesting. I haven't had a look at the topography in that area for a while. It was interesting that the advection came in from the Weddell Sea. Do you think at your location that's usually the direction of the advection, or do you also get it from, you know, the Bellingshausen, Amundsen Sea region?
Oh, it is not common. At that site in the central of Western Antarctica, most of the wind are katabatic wind. So 90% comes from the Antarctic plateau. But when we have some of these very energetic systems flowing around, they can migrate into the center of Antarctica, most of them coming from the diurnal mode land. So if they are not katabatic, it comes from diurnal mode land. So most of the cases, but that was quite exceptional, because coming in that direction, because it left the South Pacific and then crosses the Drake, crossing the Antarctic Peninsula, and migrating through the Weddell Sea until the Western Antarctica, Central and Western Antarctica. So this kind of episodes, they are not usual, they are quite unusual. And I think that this kind of air mass migration occurred because of a combination of low and high pressure systems that was acting near the Weddell Sea, and it favored the intrusion of the air mass. So that's we have in our statistics of 10 years, this kind of event are very unusual. which is doesn't occur very frequently, but well, it is 10 years of observation only, but maybe we don't know that. Also, if you can see that in that sector in June, there was a very important decline in sea ice in the Weddell Sea. There was a very important sea ice decline. And we don't know if the sea ice decline in the Weddell Sea is a consequence of the transport of moisture and heat, or the contrary. So that is something that should be investigated later. So that is very unusual system, but it gets a lot of energy to get inside.
Okay. Very interesting event, I must say.
Yeah, for sure.
Okay, all right. So Adriana, I think we're just about at the end of time here.
Yeah.
And
we can encourage our attendees to look at the poster sessions, because we got e-posters, so they can look at it and interact with the authors.
Okay, and there's no Q&A. Okay, all right. Well, thank you to all the presenters for a very interesting series of talks today, and we appreciate your contribution to this session on polar meteorology. And yes, I think we're done for the day. And have a good rest of your day wherever you are on planet Earth. Okay, bye-bye, everybody.
Bye-bye, David. Adriana.
Thank you.
Bye.
Bye.
Bye-bye.
Bye-bye.